Imagine a world where the sun never sets on half the planet, burning endlessly in a copper sky, while the other half remains locked in eternal night, ice crystals dancing in perpetual darkness. This isn't science fiction. It's the reality for most potentially habitable exoplanets in our galaxy, worlds called tidally locked planets, where one hemisphere always faces their star, while the other turns its back to the cosmic cold. What if our ancestors had emerged not on Earth, but on such an alien world? How would millions of years of evolution have sculpted humanity into something both recognizable and utterly transformed? The scientific foundation for this extraordinary thought experiment lies in one of evolution's most fundamental principles. Organisms adapt to their environments through natural selection, with extreme conditions driving the most dramatic evolutionary changes. On Earth, our human ancestors evolved over the past 6 million years under constantly shifting environmental pressures, ice ages, volcanic winters, droughts, and floods that selected for adaptability, intelligence, and social cooperation. These environmental stressors didn't just shape our bodies, they forged our minds, our societies, and even our genes in ways we're only beginning to understand. Research shows that some of the most significant evolutionary leaps in human development occurred during periods of the most severe climate instability, suggesting that environmental pressure isn't just an influence on evolution. It's the sculptor's chisel that carves new species from the raw material of genetic variation. But what happens when we take these evolutionary principles and apply them to a world unlike anything in Earth's history? Consider TRAPPIST-1, a real star system 40 light-years away, where several Earth-sized planets orbit so close to their dim red dwarf star that they've become tidally locked. Recent observations from the James Webb Space Telescope suggest that at least one of these worlds, TRAPPIST-1e, might possess a nitrogen-rich atmosphere potentially suitable for life. This gives us a real-world template for imagining how evolution might unfold on such an alien stage. On a tidally locked world, the fundamental challenge facing any evolving species would be the planet's extreme temperature gradient. A blazing day side that could reach temperatures exceeding 800 degrees Celsius, a night side that plunges to -200 degrees Celsius, and a narrow twilight zone called the Terminator line, where temperatures might allow liquid water to exist. This Terminator zone, a ring of perpetual sunset and sunrise circling the planet, would become humanity's evolutionary cradle. Here, in this narrow band where the eternal dance of light and shadow creates the only habitable conditions, our species would face selective pressures unlike anything experienced on Earth. The first and most profound adaptation would involve our circadian rhythms, those internal biological clocks that regulate sleep, hormone production, and countless other physiological processes. On Earth, our ancestors evolved intricate biological timekeeping systems synchronized to a 24-hour day-night cycle, with the suprachiasmatic nucleus in our brain acting as a master conductor, orchestrating our body's daily symphony. But on a tidally locked world, there would be no day-night cycle, only regions of permanent light, permanent darkness, and the twilight zone where our species would likely evolve. Research on circadian disruption reveals the profound challenges this would present. Studies show that constant light exposure leads to severe physiological stress, depression, hormonal imbalances, and metabolic dysfunction in Earth organisms. However, some Arctic animals demonstrate that evolution can find solutions to such challenges. Certain species show remarkable flexibility in their circadian rhythms during periods of constant light or darkness, suggesting that over evolutionary timescales, biological clocks can adapt to radically different light conditions. Humans evolving on a tidally locked world might develop entirely new biological rhythms, perhaps synchronized not to light and darkness, but to other environmental cues, like temperature fluctuations, atmospheric pressure changes, or even social interactions with other members of their community. The extreme temperature gradients would drive equally dramatic physiological adaptations. Consider how organisms on Earth have already evolved remarkable strategies for surviving temperature extremes. The Saharan silver ant can survive temperatures exceeding 50 degrees Celsius through specialized heat-reflective hairs and rapid movement patterns, while emperor penguins endure Antarctic winters through communal huddling behavior and extraordinary metabolic flexibility. Antarctic fish have evolved antifreeze proteins in their blood, and tardigrades can enter cryptobiotic states that allow them to survive temperature extremes that would kill most life forms. But the temperature challenges on a tidally locked world would dwarf anything found on Earth. Humans evolving in the Terminator zone would face the constant threat of death from wandering too far toward either extreme. Natural selection would favor individuals with superior thermoregulatory abilities, perhaps dramatically enlarged cardiovascular systems capable of rapidly shunting blood between core organs and extremities, or specialized countercurrent heat exchange systems like those found in Arctic mammals, but far more sophisticated. Their metabolism might become incredibly flexible, able to shift between high-energy states when exposed to warmth and near hibernation modes when temperatures dropped. The skin of these evolved humans might develop remarkable adaptive properties, perhaps specialized cells capable of rapid color changes to reflect or absorb heat as needed, similar to how some desert lizards regulate their body temperature through color modulation. Their hair might evolve into something more like the specialized thermal regulatory fur of Arctic mammals, potentially even developing hollow fibers for enhanced insulation, or becoming highly reflective to bounce away excess radiation from the day side. Perhaps most intriguingly, the constant environmental pressure of living in such a narrow, habitable zone would likely drive unprecedented social evolution. Research suggests that environmental challenges requiring resource sharing and cooperation have been key drivers in human social development. On a tidally locked world, survival would depend absolutely on maintaining precise positions within the Terminator zone and sharing knowledge about safe migration routes as the habitable band shifted with seasonal changes or orbital mechanics. This would select intensely for enhanced communication abilities, perhaps leading to the evolution of more sophisticated vocal or even biochemical communication systems. These humans might develop an almost hive-like social intelligence, with individuals specialized for different environmental monitoring tasks. Some adapted to venture briefly into the hot zones to scout for resources, others specialized for cold side exploration, still others serving as biological weather stations, capable of sensing minute atmospheric changes that herald shifts in the Terminator zone's position. Their languages might evolve complex grammatical structures for precisely describing thermal gradients, wind patterns, and other environmental conditions critical for group survival. The visual systems of these evolved humans would necessarily adapt to the unique lighting conditions of their world. Living in perpetual twilight, they might develop dramatically enlarged eyes, perhaps with reflective layers like those found in nocturnal animals to maximize light sensitivity. Their pupils might become capable of far more extreme dilation and constriction to handle the occasional venture toward brighter or darker zones. Some individuals might even evolve the ability to see into infrared wavelengths, giving them crucial thermal vision for navigation and environmental assessment. Consider also how reproduction and child-rearing would evolve under such conditions. The narrow habitable zone would make long-distance mate selection impossible, potentially leading to highly structured social systems for preventing inbreeding while maintaining genetic diversity within small, geographically constrained populations. Pregnancy and child-rearing would become community responsibilities of the highest order, as losing young individuals to temperature exposure would be catastrophic for small populations. These humans might evolve extended family structures with multiple adults sharing parental responsibilities, or even physiological changes like extended pregnancy periods to ensure offspring are born with better thermal regulation capabilities. The technological development of such a species would likely focus intensively on thermal management and environmental monitoring. Where Earth humans developed agriculture, tidally locked humans might develop sophisticated portable thermal regulation technologies, perhaps biohybrid clothing systems that actively manage body temperature, or architectural techniques for creating mobile settlements that could migrate with optimal thermal conditions. Their mathematics and sciences would likely be extraordinarily sophisticated in areas related to thermodynamics, atmospheric physics, and biological systems management, potentially surpassing Earth-human development in these specific domains, while perhaps lagging in others less crucial for survival. Over millions of years, the most fascinating possibility is that multiple human subspecies might emerge, each adapted to different aspects of the Terminator zone environment. There might be Twilight walkers, adapted for life in the central Terminator zone, with moderate thermal tolerances but exceptional environmental sensing abilities. Heat runners might evolve for brief forays into the dayside, smaller, more heat-tolerant, with specialized cooling systems and perhaps even behavioral adaptations for rapid resource gathering in extreme conditions. Ice climbers could develop for cold-side exploration, with enhanced insulation, modified circulation systems, and perhaps even some form of natural antifreeze chemistry in their blood. Yet despite these dramatic adaptations, these evolved humans would still face the same fundamental challenges that drive all evolution: finding resources, avoiding predators, reproducing successfully, and passing on their genes to the next generation. The extreme environment would simply create new selective pressures that sculpt different solutions to these eternal biological imperatives. Their enhanced social cooperation, sophisticated environmental sensing, and remarkable physiological flexibility would represent the same kind of adaptive responses that allowed Earth humans to colonize diverse environments, from tropical rainforests to Arctic tundra, just taken to extraordinary extremes. The question of whether such evolved humans would still be recognizably human touches on fundamental questions about the nature of our species. If we define humanity by our capacity for complex reasoning, social cooperation, technological development, and cultural transmission, then these tidally locked descendants might be more intensely human than we are, having evolved these traits to even higher levels under extreme selective pressure. Yet their physiology, behavior, and entire relationship with their environment would be so radically different that they might seem like beings from another world entirely, which, of course, they would be. This thought experiment reveals something profound about the nature of evolution itself. Life finds a way, but the ways it finds are constrained by the specific challenges each environment presents. The same evolutionary processes that shaped us on Earth would shape our descendants on a tidally locked world, but the different environmental pressures would sculpt entirely different solutions. In understanding how drastically different our species might have become under different conditions, we gain new appreciation for the specific combination of environmental factors that made us who we are today, and perhaps new insight into the incredible diversity of forms that intelligence and consciousness might take throughout the universe. The story of humans evolving on a tidally locked world ultimately reminds us that we are not separate from nature, but products of it, shaped by every environmental pressure our ancestors faced across millions of years of evolutionary time. Whether under the light of our familiar sun or the eternal twilight of an alien world, evolution would continue its patient work, crafting new forms of humanity adapted to whatever challenges the universe might offer.